On August 12th, the sky over a stretch of Europe is going to go completely dark in the middle of the afternoon. This will be the first time mainland Europe has experienced a total solar eclipse in 27 years. If you're watching from the United States, I need to tell you something up front that most headlines are not being clear about. It's the percentage of the sun the moon will cover from your location, determining if you'll witness a dramatic sight or something more subtle. If tracking real astronomical events interests you, subscribing costs nothing, and it means you won't miss the next one. There are 2 more eclipses touching this exact same region in the next 2 years alone. Let's start with the plain truth. If you are in the continental United States, you will not see totality, not from New York, Boston, or anywhere in the lower 48. What Americans will get is a partial eclipse, visible only from parts of the country. In New York, the moon covers roughly 18%. Unless you're looking with proper eclipse glasses, you likely wouldn't even notice anything unusual happening in the sky that afternoon. This is not the kind of eclipse that darkens the sky or drops the temperature like a total eclipse does. It's a quiet event. So where does the real show happen? The path this eclipse takes is one of the strangest in recent memory. It begins in the Taimyr Peninsula in Siberian Russia, a remote Arctic tundra. Here the sun never fully sets in mid-August. The eclipse begins right as the sun briefly dips toward the horizon, before immediately climbing back up at 1 minute before midnight. From there, the shadow arcs over the North Pole, sweeping down onto Greenland, Iceland, and crossing the open North Atlantic. It finally makes landfall on mainland Europe across northern Spain, the Balearic Islands, and a small corner of Portugal. The path of totality is narrow on a planetary scale, roughly 260 to 294 kilometers wide. Step outside that band, and you're back to a partial eclipse, similar to what New York and Boston will experience. Totality lasts up to 2 minutes and 18 seconds. In Reykjavik and across Spain, it will range from 90 seconds to 2 minutes. The last total solar eclipse visible from mainland Europe happened in August of 1999. Since then, 18 total eclipses have occurred elsewhere. This is the first time in 27 years that a total solar eclipse has actually crossed mainland European territory where millions live. Astronomers predict this down to the exact second using the Saros cycle, a pattern of roughly 18 years identified over 2,000 years ago. Modern astronomers combine that ancient pattern with precise gravitational calculations to predict eclipse paths centuries into the future. Eclipses have also turned into citizen science opportunities. During the 2024 eclipse, amateur radio operators studied how sunlight affects the ionosphere. Sunlight keeps the upper atmosphere ionized. Totality provides a rare experiment by switching that process off for a few minutes. A solar eclipse happens when the moon passes between Earth and the sun, and its shadow falls onto Earth's surface. Total eclipses only happen when the geometry lines up perfectly, and the shadow is tiny compared to the planet itself. That's why the path is only a couple hundred kilometers wide, rather than covering an entire hemisphere. Get ready for August 2026. Inside that narrow path, during the 1 to 2 minutes of actual totality, the moon completely blocks the bright surface of the sun. Something genuinely only visible during a total eclipse becomes visible. The corona, the sun's outer atmosphere. It is a faint, wispy, silvery white halo of superheated plasma extending outward from the blocked disk. Under normal daylight conditions, the sun's surface is so bright that the much fainter corona is completely washed out and invisible. Totality is genuinely the only natural circumstance under which the human eye can see it directly, without specialized instruments. It's worth understanding just how scientifically valuable that brief window of visible corona has actually been throughout history. Total eclipses aren't just a spectacle, they've repeatedly produced genuine scientific discoveries that were essentially impossible any other way. The element helium was first identified during the total solar eclipse of 1868, detected years before it was ever found on Earth. This is precisely why it carries a name derived from Helios, the Greek word for sun. One of the most famous confirmations in physics happened during the total eclipse of May 1919. Astronomers measured starlight bending around the sun's edge, providing evidence for Einstein's general theory of relativity. Until that moment, the theory had existed only on paper. This eclipse changed physics forever. Einstein's theory predicted that massive objects like the sun should actually bend the path of light passing near them. This claim sounded almost absurd and was essentially untestable under ordinary daylight conditions. Starlight anywhere near the sun is completely overwhelmed by the sun's own brightness. Totality solved that problem perfectly. With the sun's disk blocked, Arthur Eddington led expeditions to photograph stars that appeared behind the sun's edge. He compared their positions against where those same stars appeared months later when the sun was nowhere near them. The stars had shifted position by almost exactly the amount Einstein's equations predicted. That observation transformed Einstein from a respected physicist into an international scientific celebrity almost overnight. Modern solar physicists still use eclipses like this to study the corona's structure and temperature today. Specialized instruments, called coronagraphs, can't fully replicate what a genuine total eclipse reveals. There are two specific visual moments eclipse chasers watch for right at the edges of totality. Sunlight breaks up into a scattered string of brilliant points called Bailey's beads, named after Francis Bailey. As that string collapses to a single point, it produces what's known as the diamond ring effect. This striking sight marks the beginning and end of totality and is a favorite for photographers. Faint, wavy bands of light and shadow, called shadow bands, sometimes ripple across flat surfaces. They move in a pattern similar to the shimmer you'd see at the bottom of a swimming pool. These are caused by atmospheric turbulence distorting the thin, crescent-shaped sliver of sunlight remaining. Total solar eclipses are rare due to a genuine coincidence baked into the solar system's geometry. The sun is 400 times wider than the moon, but also 400 times farther away from Earth. No other planet in the solar system has a moon that creates this precise coincidental fit. The sun's surface sits at 500 degrees Celsius, but the corona somehow runs far hotter, over 1,000,000 degrees. This is known as the coronal heating problem, a mystery that scientists are still trying to solve. During a partial eclipse, daylight barely dims because the sun is so intensely bright. In the final moments of totality, the sky rapidly darkens, temperatures drop, and stars become visible. Birds return to roost as though evening arrived, and nocturnal insects begin their calls early. Totality is a full sensory experience, a physical reminder of the natural world's response to the heavens. Now here's a critical safety point I need to be direct about, whether you're watching a deep partial eclipse from Boston or standing inside the path. At every point during the eclipse except the It's worth explaining that annular eclipse distinction briefly, since it's going to come up again with that 2028 event. The moon's orbit around Earth isn't a perfect circle. It's slightly elliptical, meaning the moon's distance from Earth varies over each orbit. When a solar eclipse happens while the moon sits closer to Earth, it appears large enough to completely cover the sun. This produces the total eclipse and full corona we've been describing, with ethereal light streaming from behind the lunar disk. When an eclipse happens, while the moon sits farther away, it appears slightly too small to fully cover the sun's disk. This leaves that bright ring, called an annulus, visible around the edge for the entire duration of the event. Annular eclipses are beautiful, but they never produce the darkness or the safe naked-eye viewing window of a true total eclipse. So here's the honest, complete picture of what's actually happening in the sky 6 days from now. A total solar eclipse will trace an unusual path arcing directly over the North Pole, beginning just before midnight. It will cross Greenland and Iceland and make its most significant landfall across mainland Spain for the first time in 27 years. If you're in the United States, you'll see a subtle partial eclipse, roughly 18 to 27% coverage, depending on your location. You will need certified eclipse glasses the entire time to view it safely from anywhere in the US. The moon's shadow is going to trace a path over the North Pole that most of the planet will never even notice. Your experience depends entirely on which side of a 260-kilometer line you happen to be standing on. Now, if you're in the US, are you going to catch the partial version or save your attention for 2027? Drop your prediction in the comments and tell us if you're flying to Iceland or Spain for totality itself. NASA and the ESA often provide live broadcast coverage, streaming footage of the diamond ring effect and visible corona. It's a reasonable way to witness the spectacle in real time, even from a living room in Ohio or Texas. Spain is having a remarkable run. Total eclipses in 2026 and 2027, then an annular eclipse in 2028. Subscribe so you don't miss that final update before the shadow arrives. We'll see you in the next one.